Okay, welcome back. We're going to continue with the Malthusian model. So, we were just here. Okay, so obviously then when we solve for the steady state, we are after clearly expressing the endogenous variables in terms of parameters, right? So you find L star as a function of parameters, and you find W star as a function of parameters. Again, we are assuming that technology is also as an exogenous variable in this model. It converges to some finite level. Now, this tells you itself something very important about the dynamics of pre-industrial economies, right? Now, imagine, okay, so imagine that there is a change in technology, okay? Suppose that productivity increases. So what's the effect of this on the wages in the short run? Well, it is positive, right? And what is the effect of this? In fertility, it is also positive. Why? Because now the economy is more productive, people have more resources, so they procreate more. But in the long run, there is no effect. Okay? W star does not depend on AT. Okay? It stays the same. What about the population effect? Well, initially, there is no impact because LT is predetermined at T, but LT plus 1 will be larger, okay, because of the fertility effect. And in the long run, L star will be larger, okay? So technologically more sophisticated economies in the very long run, compared to technologically less sophisticated economies, will have larger populations, but they will have similar living standards if rho and gamma are similar. Okay, so if suppose that there are two empires, let's say Chinese Empire and the British Empire. Okay. Now, if these countries, so we know that X levels are different, right? We may also imagine that A levels could be different. Okay. So these differences, so if these are different and gammas are similar, if gammas and rhos are similar, what happens? Well, population levels in the long run will be different. And in the historical example, we see much larger population level in China, but income levels, living standards will be similar because those depend on the cost of children and the utility associated with, you know, the preference parameter associated with children. Okay, so if you think of pre-industrial societies, and if you look at the history of such economies and societies, these results make a lot of sense. Okay, there's one interesting paper by Michael Kremer, 1993, Quarterly Journal of Economics. Okay, so Kremer in this paper looks at the very, very, very long run movement of population. Okay, like starting at thousands of years ago, or 100,000 years ago, or something like that. Okay, so he finds when you endogenize technology with population, he finds that there is a scale effect in the very long run, but in the modern times, scale effects diminish as well. So it is interesting to check, but overall, this is a particular poverty trap model, right? Because even if you can get more productive from time to time, suppose that, for instance, this is the movement of AT in pre-industrial times, right? So in modern times, we understand that continuous technological progress occurs, okay? So innovations and all this stuff imply this as a growing level. Suppose that this is 1950s, okay? But before that, maybe the situation was like this. So there is one important innovation here, and then there is one population shock, so people forget that knowledge. Then there is one other advance, okay? So you may imagine some losses in time, but overall, maybe you have for a long episode, you may have no advance, no important advance. Then there will be another shift, then another shift, and that goes on. And only sometime with the Industrial Revolution, advancing technology becomes continuous, okay, sustained. So in the very long run, if you where is that? Okay. So in the long run, maybe you have something like this, okay, that trend. But in the short run, you see that type of fluctuation, okay? So so that makes a lot of sense for pre-industrial societies. Okay. How do I drop text draw? So this is free drawing, right? Okay. All right. So what else we have for today? Now we're gonna look at. Now we're gonna extend this particular setup with education and human capital. All right. So this is again Becker, Barrow, and Tamura, 1990. Interesting model. It includes a dynamic programming approach because parents now care about the welfare of their children as well, right? So for this, we introduced dynastic preferences, but let's look at first the similarities with the earlier setup. So the generation, so the demographic setup is very similar. There's again a discrete time framework. So there are children and there are adults. So these two generations overlap in any particular period. So the main differences are the following. We introduced time costs as well. So for reproduction, it is not enough to feed the kids, but you also spend some time with them, okay? And that time investment is for two reasons. One is nursing, right? So you have to feed the kid, you have to spend some time, feeding the kid, sleeping him or her, other stuff. And there are also goods costs, okay? You have to purchase the stuff that the baby or the kid will consume. Another main difference, as I said before, parents care about the welfare of their children. So this creates a dynamic problem, the dynamic optimization problem, obviously. And time has an alternative use. In the earlier model, in the simple multi-sim model, people only work, but here people can use some of their time to educate their kids. And if you spend a larger amount of time to educate your kid become more skillful. All right. So how do we model these things? Well, we're going to introduce dynastic preference. So this is important because next week we're going to also study dynastic preferences models and models with dynastic preferences. So it's better you pay attention to this one. So here, T denotes the generation T. All right. So generation T utility is denoted by VT. That depends on period utility, obviously, UT. So there's this period utility you obtain from consumption, as in the earlier model. And there is also this dynamic component, the dynastic component. Why is it there? Because in the next period, in the next generation, the kids will have some welfare level, and that welfare level is important for the welfare of the parent. So if I use my annotation, so let's make it blue. So this part is the welfare of one kid, okay? This part is the welfare of all kids, right? So here, kids are similar or identical. Okay, so each will have VT plus 1 level of welfare. So if you have NT kids, the total welfare of your kids will be NT times VT plus 1, and you still kind of discount it, right? So this is the simplifying assumption, but also not completely unrealistic. Why? Because if you have more kids, the utility you attach to each of them plausibly decreases with the number of your kids, right? So notice that this is alpha times NT to the minus epsilon, right? So if alpha and epsilon is positive, as we assume, so if you have more kids, it kind of decreases the utility weight you attach to kids' welfares. Okay, and without epsilon, so there are versions without epsilon as well, but in those versions we usually put another altruism factor. So alpha here is for altruism. Okay. Utility function is a power function, as you see. So sigma is positive, and it actually between 0 and 1, more specifically. And that's, as you see, a dynamic program, right? So this is dynastic preferences, and it will require for us to use dynamic programming techniques. Let's continue now. Okay, so there are different constraints that the adults face, right? Now, one is the time constraint. So T is the total time endowment. T is fixed. Okay. Now, total time endowment will be spent as labor force. So this is labor supply. Okay. And the rest will be spent on kids. Now, nu is the nursing time, and HT is education. So careful, adult himself or herself spends HT units. This is the paper's original notation, by the way. I would denote this by ET, for instance, but here it is HT. So HT is the time units the adult agent spends for each kid's education. So in total, new units, new is positive as well. So new units spent on nursing, HT units spent on education for each kid. In total, this amount, NT times new plus HT, is spent for children. Okay, so T is the total time endowment. The remaining time is supplied as labor. Okay, now there is also budget constraint. In the budget constraint, typically we have consumption, that's obvious. And this is the goods cost of children. F here is also a parameter and constant. Okay, so this part is like the earlier model, right? Remember, in the earlier model, we had this consumption spending plus spending on the consumption of the kids. Now here, the income part is different, right? Why? Because in this model, there's human capital. Now, income part will have a particular parameter D, so this is constant again. LT is the labor supply, so this is the time. And this part is the human capital of the adult, of the parent. Now, human capital of the parent has two components. This is the innate component, and this is obtained through education. Obtained via education. Okay, so the innate component is there. It is the type of raw skills that everybody has. All right, so everybody has some, has some minimum level of physical and mental health. So if they are healthy enough to be a worker, then those innate abilities like eye-hand coordination, speaking abilities, other stuff, these are the raw human capital. Okay, these skills, these innate abilities define the raw skill level. Okay, the rest of it is obtained through education. Whose education? This adult's own education by his or her own parents. Okay, in the previous episode. So each generation here accumulates, of course, human capital, ideally, right? So these are the constraints that a generation T adult faces, okay? Generation T adults. Okay, so they face that time constraint and that budget constraint. Okay, and these are all parameters, and we assume that H0 is also given and constant. Okay, this is what we typically assume. So now, where do we go from this? Well, we also introduce education technology, right? In the education technology, we know that we must specify how the education decisions of the parents today for their kids affect their children's human capital, right? So here we have another constant, A. So this is the education technology, which means this is an input. This is the time input, okay? This is the time this is the allocation of time spent on kids' education, and that's the knowledge input or human capital input, right? So this is the, let's say, knowledge input. Why is that there? Because if your parent is highly skilled, then that is good for your own skills, okay? If your parent is a brain surgeon, then it is good for you to become, if you want to become a brain surgeon, then it's good for you. Here, of course, there's only one occupation, right? So all these skills are measured in all these skills are measured as one continuous variable. Okay, so possibly there is some zero level, and there is this innate level, and the education investments make them grow. So there is no multiplicity of fields or trajectories of knowledge, right? But this is the simplest way of understanding it, right? If your parent is highly skilled, and if he or she spends a lot of time on you, and if the education quality is given, this is the quality of the education technology, then you will have this particular level of human capital when you become an adult. All right. Now, we're gonna execute a change of variables, okay, to simplify the notation. So we define this new variable ZT as the total human capital. Remember, the total human capital has an innate component and an education component. Okay, so we denote the totality as ZT. So then what do we have? In the next piece, so using this education technology, we add the innate ability to both sides. Okay, then we can write this in terms of Z. Okay, and as you see, it becomes a difference equation in ZT, right? So you may actually draw it. So you have ZT here, ZT plus 1 here. This is the 45-degree line, right? And you have H0 here, okay? Now, if, so of course, the slope could be larger than 1, the slope could be equal to 1, or the slope could be less than 1, all right? What is the slope equal to? The slope is equal to A times HT, right? Because ZT plus 1 divided by ZT is A times HT, H0 divided by ZT. Okay, so the slope slope of this will be AHT, and this is the intercept, of course, and the growth. So obviously, if the slope is less than 1, there is no growth in ZT. And then for other cases, we're gonna see how we can describe growth. But if that's the case, it turns out if we can write the transition equation in this way, right, from a technical point of view, then the value function can be expressed in this way. All right. So you know this from the last semester's class. We need one state variable here, and that state variable here is obviously ZT. Okay. Now, how do we make sense of all these things? Well, this is the problem, right? So what did I do? Well, I replaced labor supply from the time constraint. This became ZT, and now I had the transition equation as well. So this is a typical dynamic program. Of course, we don't know V function. If we knew it, that would be a very nice thing, but we don't know it. Without knowing V function, how do we describe the optimal choice of a parent in generation T? So that's the obvious dynamic programming question. But this problem is simple enough to be characterized in great detail analytically. For exact solutions, you need to use technology. You need to use your typical solution methods. But for steady states, we can actually have some characterization with pen and paper. So how do we proceed? Well, obviously, we know how we can characterize the first of the conditions and the envelope condition here, but let me tell you something important. You should be careful with the non-negativity constraint here. Even if you assume consumption is always positive, and even if you assume fertility is always positive, an interesting case is that the education spending on your kids, the time you spend for educating your kids, may be zero at the optimal point. So you should, as a theorist, you may want to give this possibility. You may want to keep this possibility open to understand the issue of high fertility trap. Okay, so when we are writing the first of the conditions, we're going to be careful with this. Okay, so objective function written as a Bellman equation here, budget constraint and the transition equation. Then what do we have? Okay, first we eliminate CT for simplicity. So now the control variable is N and H. So there are two control variables, N and H, and there's one state variable, which is ZT, right? I just basically replace consumption here and eliminate the budget constraint. Then we have the necessary conditions for an optimal path. Again, be careful, we have the non-negativity constraint in terms of education investment. All right. So we assume that NT is positive. Okay. We assume that HT could be positive or zero, and this is the envelope condition, as you know, right? Using these three equations, actually one is inequality, we want to understand the different steady states. Okay, now in one steady state, let me clear these things. Now in one steady state, we have no education spending. Now what happens in that steady state? Remember that difference equation. So we have ZT plus 1 equals AHT ZT plus H naught, right? So if HT is equal to 0, obviously ZT does not change, right? And ZT is equal to ZT plus 1, which is equal to H naught. And this steady state is denoted by U for, I guess, unskilled. Okay, so ZU must be corresponding to a particular, of course, fertility level, right? Because at that steady state, if fertility is going to be positive at all times, then this means at that steady state, there will be some steady state fertility level. So how do we understand that? Well, we replace all the equations, in all the equations, we replaced fertility, right? Because these necessary conditions must hold at steady state as well. So these must be true. Okay, so these equations must be true in the steady state as well. Okay, these must hold in the steady state. So I replace fertility. I replace ZU. Okay, now since this is equal to 0, I am at the corner solution. So this inequality is there. Now, using these equations, it looks a bit complicated, but it's not actually. So using these equations, you can do what? First, you can imagine from the third equation, you may imagine that this derivative, so this is, there's a typo here, so this must be V prime, okay? So you define that, right? How do you write that? Well, clearly, it only depends on these parameters. And more specifically, it does not depend on A, right? It does not depend on education technology. Education technology parameter will be the important parameter here, okay? So we know this from equation 3. Equation 1 also has an interesting feature because ideally it tells you that fertility does not also depend on A, right? Of course, it will. It may depend on A through V, but if you express it as a result, it will not depend on A, and actually you realize that it doesn't depend on A as well, because V prime ZU is independent of A at this steady state. It will be, of course, different under the other steady state, right? But for this steady state, 3 and 1 imply these results, okay? Then, if you put these things into inequality 2, you get this result, okay? So what does it tell you? It tells you that if you denote this by, let's say, this whole thing by a threshold, you understand that there is a threshold of A, right? And if that's true, then education investment is 0. And with education investment being equal to 0, ZT is equal to ZU, NT is equal to NU. Again, to solving for NU, you need to use some numerical methods, but at least you understand that it depends critically on the education technology threshold. So what's the economic logic behind it? Well, remember that this is determining the return to education, right? This parameter determines the returns to education. And if the returns are small enough, okay, if the returns are small enough, then you don't find it optimal, right? That's obvious economic reasoning. You don't find it optimal to decrease the number of kids and increase the education time that you spend with them. All right, that's pure economic reasoning, actually. And again, even though we do not have analytical solutions for fertility that requires numerical solutions, we can still understand a parameter is critical here. So if you want education reform, you increase, for instance, in a typical underdeveloped economy, you increase A by using some education reform. And that type of education reform eventually results in lower fertility because of quality quantity trade-off. Okay. So what else do I have? Okay, so that's the last slide. Now, what happens at the other steady state, right? In the other steady state, this is positive. So you spend a positive amount of H star. Now that growth will be approximated in this way. So if you look at the paper, there's a balanced growth analysis, and that analysis eventually tells you that the growth rate of consumption is well approximated by this level. So you have the optimal education investment, which is sigma nu divided by 1 minus sigma minus epsilon. And you also have a parameter, and that gives you the endogenous growth rate of the economy, okay, in terms of consumption. And within that setup, I don't have it in these slides, but you can also, of course, find steady state fertility level, and importantly, steady state fertility level with education is lower than steady state fertility level without education. Okay, so in the paper, the authors explain how you find actually this approximation. You can actually use the methods I taught you in the last semester to come up with a solution. You can, I think it's easier with the policy function iteration here, or value function. I'm not exactly sure, but for the theoretical purposes, understanding that threshold behavior is more important for us for this class. So high fertility trap, as you see, have two different versions. I mean, there could be other versions, but these are the two most obvious. One is the Malthusian model, and the other is what we obtain when we introduce human capital to the model. So now let me stop here, and if you have questions, I can try to clarify issues.
Thank you. I have no questions.
Okay, so next week we're gonna look at some more interesting Malthusian models, let me say. Okay, so we're gonna look at how hunter-gatherer societies actually take certain allocation decisions, and how societies with two classes such as landowners and workers, how do they actually take decisions, and how the demographic and technological elements play out in such models. All right, so we're gonna make some effort to understand the mechanisms of feudal economies. So I will see you next week then. Thank you for attending.
Thank you.
All right,
Thank
bye-bye.
you.